We are tackling the human circulatory system today, but, and this is a really big but, we are not doing the high school biology version where we just say the heart is a pump and arteries are tubes.
Right.
We're zooming in way, way past the heart. We're looking at the absolute edge of the network. We're asking, how does your body manage to distribute blood flow perfectly to, what, 100 trillion separate cells all at the same time?
And without the brain having to micromanage a single one of those connections.
Yeah. Exactly. I mean, just think about the computing power that would require. If you had to consciously decide, okay, divert a little more flow to the left pinky, now back to the stomach, now a bit more to the calf muscle, your brain would crash in a millisecond.
It's the ultimate decentralization problem. It really is. It's a computing problem as much as it is a biological one. You have a central pump, the heart, but it's just providing the pressure. It has absolutely no idea where that blood is actually going.
No idea.
Doesn't know if you're running a marathon or, sitting on the couch eating a pizza.
And when I was going through the research for this, the thing that kept hitting me over and over was the sheer scale of the stakes. If this system fails for even a few minutes, tissues start to die. Yet there is no central controller. So who is steering the shit?
Who's in charge?
That's what we're figuring out today. We're looking at how the tissues themselves, the locals, take control of the tap.
And to understand who is steering, you really have to understand the constraint, the why behind the design. And it all starts with a really shocking set of numbers regarding our muscles. This is what we're calling the problem of scale.
Yeah, walk us through this, because this was the first thing in the notes that really made me sit up straight. It completely reframed how I see the body.
So think about your body mass. For the average person, skeletal muscle, your biceps, your quads, your hamstrings, basically the meat on your bones, makes up about 30 to 40% of your total weight.
It's a huge chunk of you.
It's the biggest organ system by mass, by far. It's the engine.
Right. It's the engine.
But when you were just sitting here recording this, or when you're sitting at your desk or driving, those muscles are metabolically dormant. They are, for all intents and purposes, sleeping giants. They receive a tiny, tiny trickle of blood.
Just a trickle.
The data shows about 4 milliliters of blood per minute for every 100 grams of muscle.
Which is, that's nothing. I mean, 4 milliliters is less than a teaspoon.
It's barely enough to keep the pilot light on. The muscle is essentially in standby mode. But let's say you suddenly decide to sprint to catch a bus, or you're in the gym and you start a heavy set of squats.
Right.
The metabolic activity in those muscles just explodes. It jumps 60-fold, instantly.
And obviously the fuel line has to open up with it.
It has to open wide. The demand for blood flow increases 20-fold. So we go from 4 milliliters up to 80 milliliters per minute per 100 grams. That is a massive dynamic range.
I can't think of a single machine that idles at 4 and then ramps to 80 in, 3 seconds without blowing a gasket.
And that leads to the logical problem, the obvious question. If the body is physically capable of delivering 80 milliliters, if the pipes are wide enough to handle that volume, why don't we just run it at full capacity all the time?
Yeah, why bother?
Why bother with all this complex switching and throttling? Just open the taps and be safe, right?
Right. I mean, usually in engineering, you build for the peak load and you just leave it there. It seems so much safer than trying to adjust constantly. Why would you ever risk starving a tissue?
It would be safer for the tissues, maybe, but it would be absolutely catastrophic for the heart. This is the ultimate efficiency hack. If every single tissue in your body, from your gut to your muscles to your skin, demanded its maximum blood flow simultaneously,
At the same time?
the total flow requirement would just be astronomical.
I try to do the back of the napkin math on this based on the cardiac output numbers. A normal heart pumps, 5 liters a minute at rest?
Roughly, yes,
Yes.
at rest. And maybe 25 or 30 during extreme exercise for a trained athlete.
But if everything opened up at once, every capillary, every arterial, every vessel, the math suggests you'd need a cardiac output of something like 200 liters per minute just to keep the pressure from collapsing.
Which is physically impossible. The heart would essentially work itself to death in minutes trying to move that much mass. Or, more likely, your blood pressure would just drop to 0 because the volume is spread too thin.
It's like trying to power a whole city with a single car battery.
Exactly. It's like trying to power a skyscraper with a portable generator. So the system is built on scarcity. It's built on the idea that not everyone can eat at the same time.
So it relies on tissues being selfish.
Precisely. And that's the mission of this deep dive.
Right.
We are going to explore local and humoral control. We're going to break down how tissues selfishly manipulate their own blood supply without ever asking the brain for permission. We're going to look at the acute mechanisms, what happens in seconds, and then the long-term construction projects that happen over weeks and months.
So let's start with the philosophy of this local control. The source material called it minimalist regulation, which I loved. The rule is, take the absolute minimum blood flow required to sustain function. No more, no less.
And no more, no less is really the key. It's a minimalist philosophy. By keeping flow at the absolute minimum necessary, the body ensures the heart isn't overworked. It preserves the cardiac reserve for when you actually need it, like when you're running from that bus.
But need is subjective, isn't it? I mean, I was looking at the breakdown of flow by organ in the source material, and there are some real divas in the human body. Most tissues just want the basics, oxygen, glucose, take out the trash. But then you look at the kidneys.
Oh, the kidneys are the heavy hitters.
Yeah.
They're absolutely the divas.
They are getting 1,100 milliliters per minute. They're tiny organs, relatively speaking, but they're just drinking from the fire hose. That's a huge amount compared to resting muscle.
It is. But that's a perfect example of distinguishing between a survival need and a functional need. The kidney tissue itself, the actual cells that make up the organ, doesn't need that much oxygen to survive.
So the cells would be fine with less.
Oh yeah, if you gave them just a fraction of that blood, the cells would live. But the job of the kidney isn't just to stay alive. Its job is to filter the blood.
It's a treatment plant.
Exactly. It's a filtration plant.
Yeah.
And you can't filter the water if you don't divert the river through the plant. They need that massive flow to scrub the waste products and regulate your body fluid volumes. If you drop the flow to the kidneys, to just what keeps the cells alive, you die of uremic poisoning because the blood wouldn't get cleaned.
And it's a similar story for the skin, right? The skin isn't just a wrapper, it's a radiator.
The skin is fascinating. Its blood flow has almost nothing to do with actually feeding skin cells. I mean, skin cells are pretty tough. They don't need all that much. The flow is all about thermodynamics.
Temperature control.
Purely. If you're hot, we open the valves to the skin to dump heat into the environment. If you're cold, we clamp them shut to preserve the core temperature.
So the skin cells are just kind of along for the ride.
Essentially. The need in that case is defined by the organism's temperature, not by the tissue's hunger.
And the liver, that was another big one?
The metabolic factory, 1,350 milliliters per minute. It's processing nutrients from your lunch. It's detoxifying chemicals. It needs that high flow to perform all those chemical reactions.
Okay, so we have the ground rules. The body is a miser. It only gives you what you need to do your job, but not a single drop more. So now let's get into the mechanics of how a specific tissue argues its case. Let's say I'm a bicep muscle. I start curling a dumbbell. I need more blood immediately. How do I get it?
And this brings us right to segment 2, acute control. This is the rapid response team. We are talking about changes that happen in seconds to minutes.
And this is all happening at the level of the microcirculation, right? We're talking about the tiniest arterioles and the capillaries themselves.
Yes. And specifically, I want to introduce a structure called the precapillary sphincter.
I love that word, sphincter. It just sounds exactly like a gatekeeper.
It effectively is. It's a tiny, tiny band of smooth muscle that's wrapped around the entrance to a capillary. Imagine a garden hose with a little clamp on it. If you tighten the clamp, that's the sphincter contracting, the water stalks. If you loosen it, the water flows.
Right.
The million-dollar question in physiology for decades has always been, who loosens the clamp?
Because there's no nerve ending there from the brain saying, open up now.
Exactly. It's all local. The text presented two main theories here, and honestly, they seem to act like two sides of the same coin. The first one is the metabolic theory.
This is the trash can theory, if you want a simple visual for it.
Okay, walk me through your trash can analogy. I like that.
So your bicep muscle starts working hard. It's burning energy. When you burn fuel, you create exhaust. In the body, that exhaust takes the form of metabolic waste products, carbon dioxide, adenosine, potassium ions, hydrogen ions, which is basically acid.
Correct. A whole soup of them.
So the cell is working hard, and it becomes surrounded by a cloud of this exhaust.
Exactly. And this exhaust isn't just waste, it's a signal. These chemicals are all potent vasodilators. As they accumulate in the fluid around the blood vessel, they physically touch the smooth muscle of that precapillary sphincter. And their chemical message is simple: relax.
That is just brilliant. The pollution itself is the key that unlocks the fresh air.
It is. It's a perfect negative feedback loop. As the waste builds up, the vessel dilates, fresh blood rushes in, which then washes away the waste and brings new oxygen. As the waste clears, the signal disappears, and the vessel tightens up again.
I want to do a little deep dive on one specific chemical here because the text highlighted it specifically for the heart, adenosine.
Yes, adenosine is absolutely the star of the show when it comes to cardiac blood flow. It's the primary driver for the heart.
Why is it so special there?
It all relates to the fuel source. Heart muscle runs on ATP adenosine triphosphate. That's the energy currency of the cell. Triphosphate means it has 3 phosphates attached to it. When the heart is working too hard, or if it's not getting enough oxygen, it burns through that ATP faster than it can recharge it.
It's running down the battery.
It is. The ATP breaks down, it loses a phosphate,
Yeah.
then it loses another one. Eventually, you're left with just the adenosine part of the molecule.
And usually the cell would want to recycle that, right? You don't want to just throw away the battery casing.
Ideally, yes. You'd want to rephosphorylate it. But in a crisis, when oxygen is low, the cell can't hold on to it. The adenosine actually leaks out of the heart muscle cell. It drifts over to the coronary arteries, and it binds to receptors that trigger an immediate, powerful dilation.
It's a distress flare.
It's the cell screaming, "I am running on fumes, open the floodgates now." And it works. The coronary arteries dilate, blood flow surges, oxygen arrives, and the cell can start rebuilding its ATP. It's a lifesaver.
Okay, so that's the metabolic theory. The waste signals the need. But there's a second theory that felt, I don't know, more mechanical, the oxygen demand theory. Or I guess the nutrient demand theory.
This one is fascinating because it relies on the weakness of the muscle itself.
Right, because we have to remember that sphincter is a muscle, and it takes energy for it to stay clenched shut.
Exactly. Think about holding a heavy weight. It takes constant energy just to keep holding it. Keeping a door slammed shut against blood pressure takes effort. The smooth muscle cells that form that sphincter need oxygen and nutrients just to maintain that contraction, that tone.
So if the bicep cells all around the sphincter are just gobbling up all the available oxygen.
Then there is no oxygen left for the sphincter itself.
Yeah.
It literally runs out of gas. It loses the strength to stay contracted. It relaxes, not because some chemical told it to, but because it's starving and weak.
And the moment it relaxes, the door swings open and blood rushes in.
Which brings oxygen. The sphincter takes a deep breath, refuels, gets strong again, and clamps shut.
And this is what creates that cycling effect mentioned in the notes. Vasomotion.
Yes. If you look at capillaries under a microscope, they aren't just open or closed all the time. They twinkle. They cycle open, close, open, close. The more oxygen the surrounding tissue needs, the longer they stay open during each one of those cycles.
So asking which theory is the right one, metabolic or oxygen demand, is kind of a false choice.
It is. It's almost certainly both working in concert. It's a fail-safe system. Redundancy is the hallmark of biology, right? If one system fails for some reason, the other ensures the tissue doesn't die. It's a robust network. And it's not just oxygen, lack of glucose, amino acids, or fatty acids can also trigger this. So if the pantry is empty, the door opens. It's that simple.
I like that it's robust. Now, let's look at some real-world examples of this acute control in action, because the text gave us 2 terms that sound kind of fancy but actually explain things we feel every day: reactive hyperemia and active hyperemia.
Let's start with reactive hyperemia. You definitely felt this if you ever sat on your foot until it went numb.
The dead leg, oh yeah. Or if you wrap a rubber band too tight around your finger.
Right, so you've compressed the arteries, you've occluded the flow. For maybe 10 minutes, your foot got almost no blood. But the cells were still alive, they were still metabolizing, albeit very slowly. And in that time, they were building up a massive oxygen debt.
And all those waste products were just piling up because there was no flow to wash them away.
Exactly. So the moment you stand up and release that pressure, the floodgates just burst open. The vessels are wide open from all those vasodilator signals. Blood flow doesn't just return to normal, it surges to 4, 5, maybe even 7 times the normal rate.
And that's that intense pins and needles feeling, that rushing warmth.
That is reactive hyperemia. And the really cool thing is, the duration of that surge is perfectly calibrated. It lasts just long enough to exactly repay the oxygen debt that built up. Once the cells are topped up and the waste is washed out, the vessels constrict and flow goes right back to baseline.
It balances the checkbook and then it closes the account.
Perfect analogy. Now, active hyperemia is what happens when you hit the gym. There is no blockage. There is just massive, massive demand.
The pump.
The pump, exactly. You start lifting weights, the demand skyrockets, the cells devour oxygen like crazy, they dump adenosine and CO2 and acid, the vessels dilate massively to sustain that new, higher level of work. In skeletal muscle, we can see up to a 20-fold increase in flow.
So reactive is repaying a past debt, active is funding a current spending spree.
That's a great way to put it. Active hyperemia sustains the high function.
Okay, so that covers how tissues ask for more blood. But there's this other concept in the notes that I found really, really counterintuitive: autoregulation.
Ah, yes. This is where engineering, intuition, and biology collide.
Yeah. Normally I think of plumbing.
Hmm.
If I increase the pressure at the water main, the flow out of my faucet increases. High pressure equals high flow. Simple.
Correct. That is basic physics. It's Ohm's law for fluids.
But autoregulation says if your blood pressure spikes, say you get stressed, and your arterial pressure goes from 100 to 150, the flow to your tissues spikes for just a second, but then almost magically it clamps back down to normal, even though the pressure is still screaming high.
It essentially ignores the driving pressure in order to maintain a constant flow. It's bizarre.
Why would it do that? Why not just enjoy the extra flow?
Because the tissues are delicate, especially the capillaries. I mean, they are one cell thick. If you hit them with 150 millimeters of mercury of pressure constantly, you risk blowing them out. You risk edema fluid leaking out into the tissue, or you just risk washout, stripping away necessary nutrients and signaling molecules too fast.
So the body needs a surge protector.
Exactly. And there are two main theories on how this surge protector works. One is metabolic, similar to what we just discussed. High flow provides too much oxygen and washes away the vasodilators so the vessels naturally constrict. But the second theory is unique to autoregulation. It's called the myogenic theory.
This is the stretch reflex.
Yes. It turns out smooth muscle has this built-in personality trait. It hates being stretched. If you push on it, it pushes back.
Like a spring, or like a cat you're trying to put in a carrier.
Like a loaded spring is a great way to think of it. When that high blood pressure hits the wall of the arteriole, it physically stretches the vessel wall. The smooth muscle cells sense this stretch, and they immediately reflexively contract. They clamp down.
So the pressure is trying to force the vessel open, and the vessel's response is to squeeze even harder to shut.
And by squeezing shut, it increases its resistance to flow. The higher resistance perfectly offsets the higher pressure, and the flow creates a flat line. It stabilizes, it keeps the fragile capillaries downstream, safe from the storm that's occurring in the main arteries.
It's amazing that this isn't the brain doing it. It's not a hormone. It's just the physical property of the muscle itself. It's inherent.
It's a completely decentralized safety mechanism.
But there's a catch, right?
Right.
The text mentioned that metabolic factors can override this myogenic reflex.
They absolutely have to. Think about it. When you exercise, your blood pressure goes up. The myogenic reflex would want to clamp down to fight that pressure.
Right.
But your muscles desperately need the flow. So the metabolic signal, that cloud of adenosine and CO2, shouts louder than the stretch reflex does. It forces the vessel to stay open, ensuring you get the performance you need when you need it.
So metabolic need is the trump card. It always wins the hand.
Always. Function comes first. Protection comes second.
I want to shift gears now. We've been talking a lot about the muscle of the vessel wall, but we really need to talk about the lining. The
Right.
wallpaper, so to speak, the endothelium.
This has been one of the biggest paradigm shifts in medicine in the last, 30 or 40 years? We used to think the endothelium was just a non-stick coating, like Teflon in a pan, just there to keep the blood from clotting.
And now, what do we know now?
Now we know it is a massive distributed organ. It's a chemical factory, and it holds some of the most important keys to blood flow control.
And the most famous product of this factory is, of course, nitric oxide.
NO, the relaxer. It's a gas, a tiny, fleeting little molecule.
How does the vessel know when to release it? What's the trigger?
It feels the flow, literally. The phenomenon is called shear stress. Imagine a fast-flowing river rushing through a canyon. The water drags against the rock walls. That friction, that pulling force, is shear stress.
Okay.
When blood flows fast through an artery, it drags on the endothelial cells on the surface.
It tugs on them.
It tugs on them. And that physical distortion triggers a chemical pathway. The cell takes an amino acid called arginine and, using an enzyme, converts it into nitric oxide.
NO is like a ghost, right? It passes right through cell wall.
It diffuses instantly out of the endothelium and into the smooth muscle layer right underneath. And its message to that muscle is simple: relax.
So fast flow creates shear stress, which releases NO, which widens the vessel, which would then slow the flow down.
Well, it reduces the drag.
Right.
It optimizes the pipe diameter for the amount of fluid that's moving through it. It widens the bigger upstream vessels to make sure the downstream tissues get what they need without excessive pressure. It's real-time, dynamic optimization of the whole system.
Now, we have to touch on the clinical side of this because nitric oxide is the mechanism behind one of the most famous drugs in history. We're talking about Viagra.
We are.
Like,
And also nitroglycerin for chest pain, for angina. They both work on this exact same pathway.
walk us through the chemistry because the notes got pretty specific here. It's not just NO hitting the muscle, it's a chain reaction.
It is. So NO enters the smooth muscle cell. It activates an enzyme which then produces a messenger molecule called cGMP. You can think of cGMP as the green light. As long as cGMP is floating around in that cell, the muscle stays relaxed and the vessel stays open.
But the body doesn't like permanent signals. It always needs an off switch.
Always. So there is another enzyme in the cell called PDE5, phosphodiesterase 5. PDE5 is the red light. Its only job is to hunt down cGMP and destroy it, which allows the muscle to contract again.
It's the party pooper.
It is the party pooper. Now, in conditions like erectile dysfunction, you might not be producing enough cGMP to keep the vessels dilated for long enough. Enter sildenafil Viagra.
What does it do?
It is a PDE5 inhibitor. It handcuffs the party pooper. It literally stops PDE5 from destroying cGMP.
So the green light stays on much longer.
Exactly. It doesn't create a new signal. It just amplifies and extends the natural signal that was already there. It keeps the flow open. And that same mechanism is what helps in angina, where we need to keep the coronary arteries open. Nitroglycerin basically breaks down in the body to release NO directly.
It's just incredible how specific that chemistry is. But the endothelium isn't just about relaxation. It has a dark side, too.
Endothelin.
It sounds like a supervillain.
It acts like one, but for a good cause. Endothelin is a 27 amino acid peptide, and it is the constrictor. It is incredibly potent, one of the most powerful vasoconstrictors the body makes. But usually, it's locked away safely inside the endothelial cells
So when is it released?
when the vessel is smashed. If you get in a car accident or suffer a crushing injury, a severe chemical burn, any kind of trauma that physically ruptures the endothelial cells, they break open and endothelin spills out into the tissue.
And what does it do?
It clamps the vessel shut, hard. It can cause an artery as big as 5 millimeters in diameter to go into complete spasm and close off.
Which is to prevent you from bleeding to death.
Ideally, yes.
Yeah.
It's the emergency shutoff valve. If the pipe is broken, you have to stop the water. Endothelin does that. We also see its levels are elevated in hypertension, but drugs that block it haven't really been the silver bullet for blood pressure we hoped for, though they are used effectively for pulmonary hypertension.
Okay, so we've covered right now, the acute control, the metabolites, the myogenic reflex, the endothelium. These handle all the second-by-second changes. But the notes make a very important distinction. Acute control is limited.
It is. It can only open the vessel as wide as it physically is. It can't make the vessel bigger than its own maximum diameter. Acute control handles about 75% of the necessary adjustment. But if a tissue is constantly hungry, if you start training for a marathon and your muscles are demanding high flow every single day for weeks, the body realizes, okay, simply opening the door wider isn't enough. We need to renovate.
This is segment 6, long-term regulation. And this isn't about stretching, it's about actual construction.
It's about changing the physical architecture of the system.
The primary mechanism here is angiogenesis, growing new blood vessels.
Angio, meaning vessel, genesis, meaning creation, building new roads.
And how does the body know when it's time to build a new road?
The trigger, surprisingly, is almost identical to the acute trigger. Oxygen deficiency, hypoxia.
So if a tissue is chronically short on oxygen, it starts to take action.
It sends out a chemical distress flare in the form of growth factors. VEG, vascular endothelial growth factor, is the main one. You also have fibroblast growth factor, FGF, and another one called angiogenin.
And what happens when the existing blood vessels see this VEGF signal?
It's like something out of a sci-fi movie. The endothelial cells in the nearest parent vessel dissolve their basement membrane. That's the glue that holds them in place. They start reproducing very rapidly, and they scream outward, forming a solid cord of cells that tunnels through the tissue, growing toward the source of the signal.
Like a root growing toward water.
Exactly like that. That cord then hollows out, becomes a tube, connects with another developing tube, and suddenly, snap, you have a brand new capillary loop, and blood begins to flow.
And this happens over days and weeks.
Yes, in young people, it can happen very fast. In older people, it's a bit slower. But it physically increases the density of the entire network. More pipes, more flow capacity.
This sounds purely beneficial. I mean, more flow, better performance. But the notes included a case study that was, honestly, it was quite tragic. It shows what happens when this very clever system gets confused. Retrolental fibroplasia.
This is a very somber chapter in medical history. In the mid-20th century, we had a lot of premature babies born with undeveloped lungs. To save them, doctors put them in incubators, oxygen tents, that were pumped full of 100% oxygen.
Which on the surface seems like the absolute right thing to do.
And it kept them alive. It saved their lives. But you have to remember the rule of angiogenesis. Lack of oxygen triggers growth, and abundance of oxygen stops it.
So the baby's developing eyes.
The retina is a very vascular tissue. It needs a lot of blood vessels. But in the incubator, it was bathing in pure oxygen. So the developing blood vessels in the retina said, oh, we have plenty of oxygen here. We don't need to build any more roads. In fact, existing vessels even started to degenerate. They vanished.
And then what happened?
Well, the baby gets healthy. The lungs mature. The doctors take the baby out of the tent and into normal room air.
And suddenly the oxygen level plummets.
And the retina, which now has almost no blood vessels because they stopped growing, is plunged into sudden, severe starvation. It is suffocating. So it panics. It releases massive, explosive amounts of VEGF.
And the body overreacts.
It overcompensates wildly. New vessels grow, but they grow too fast. They're disorganized. They burst out of the retina and grow into the vitreous humor, the jelly of the eye. They block light. They bleed. And the result, tragically, is permanent blindness.
It's just heartbreaking because the body was doing exactly what it was programmed to do.
The mechanism is perfect. The input was flawed. It's a powerful reminder that these systems are blind. They don't know context, they only know chemistry. The body saw too much oxygen and stopped building. Then it saw no oxygen and built way too much.
There's another side to this long-term regulation that is more positive, though. Collateral circulation. This is the body's backup plan.
This is what saves you from a heart attack if you're lucky.
Explain that. How does that work?
So if a coronary artery gets blocked, say, by a clot, the tissue downstream starts to die. But if that blockage has been happening slowly over many years, the body has already been building detours.
Side streets around the traffic jam.
Yes, collateral vessels, small connections that link the blocked artery to a healthy one nearby.
And the notes made a really interesting comparison here between a 20-year-old's heart and a 60-year-old's heart.
It's a strange and terrible irony. If a healthy 20-year-old has a sudden massive blockage of a main coronary artery, they will very likely drop dead on the spot.
Because they have no detours built.
Their arteries are pristine. They never had a reason to build a backup plan. So when the main road is cut, the tissue downstream dies instantly. But a 60-year-old who has had mild atherosclerosis for a decade, their heart has been slightly hypoxic, slightly starved of oxygen for years.
So it's been building these side roads.
It has spent 10 years building a rich, dense network of collateral vessels. So the big blockage hits, and the traffic just diverts to the side streets. They might have a mild heart attack or maybe even no symptoms at all, while the 20-year-old dies. The chronic disease prepared the older heart for the acute crisis.
That is a fascinating perspective on aging and disease. It's almost like the disease inoculated them against the catastrophe. Now, before we close out the structural stuff, we have to talk about one more form of remodeling. Vascular remodeling. This isn't growing new vessels, but changing the shape of the old ones.
This is structural engineering, and it's driven by pure physics, specifically a rule called Laplace's law.
It is with the math.
The simple version is tension equals radius times pressure.
Translation for the non-physicists.
The wall of a blood vessel is constantly under tension, being stretched by the pressure inside. The body wants to keep that tension stable. If the pressure goes up, the tension goes up. To bring that tension back down to normal, the body has to change the radius of the vessel or the thickness of the wall.
So in a condition like high blood pressure hypertension, what happens?
You get what's called inward eutrophic remodeling. The small arteries constrict to fight the high pressure. Over time, they rearrange their cells, the wall gets thicker, and the hole in the middle of the lumen gets smaller. It permanently cinches the belt tighter.
Which actually makes the hypertension worse in the long run, doesn't it? Because now the resistance is permanently higher.
It does. It's a vicious cycle. The adaptation to the pressure actually reinforces the high pressure. It's another example of the body's blind wisdom.
And what about the opposite, high flow, like in those dialysis patients you mentioned?
That's outward remodeling. If you surgically connect an artery directly to a vein, creating an AV fistula for dialysis, the flow through that vessel is massive. The shear stress is huge. The vessel responds by getting wider increasing its diameter and thickening its wall to handle the increased load. It essentially turns a garden hose into a fire hose.
It's amazing the body is constantly remodeling its own house while living in it.
It never stops. It detects the stress and reinforces the structure to match.
Okay, we've spent a lot of time in the weeds. Local control, endothelial factors, remodeling. But there is a boss. There is a global system that can override all of this when survival is at stake. Segment 8. Humoral control.
The chemical messengers that are circulating in the blood. Hormones, essentially.
Let's break these down into the emergency crew and maybe the maintenance crew.
Yeah.
Who are the heavy hitters for vasoconstriction, the ones that clamp everything down?
The biggest one is norepinephrine.
Adrenaline's cousin.
Yes. Released by the sympathetic nerves and the adrenal medulla. This is the fight-or-flight hormone. When a bear is chasing you, norepinephrine floods your system. It clamps down on blood vessels in your gut, your skin, your kidneys.
Sorry, digestion. We have to run right now.
Exactly. It shunts blood to where you need it, the muscles and the heart.
Yeah.
Epinephrine is similar, but it can actually dilate the heart vessels while constricting others, which is interesting. Then you have angiotensin II,
The blood pressure regulator.
the master blood pressure regulator. It constricts arterioles everywhere to raise your total peripheral resistance. It's also crucial for preventing sodium and water loss in the kidneys.
And the nuclear option, vasopressin.
Vasopressin, or ADH, antidiuretic hormone. This is the I am bleeding to death hormone. If you have a severe hemorrhage and lose a lot of blood, the pituitary gland dumps vasopressin. It causes a massive systemic clamping of the vessels. It squeezes every last drop of blood out of the periphery to keep the brain and heart alive.
Wow.
It is even more powerful than angiotensin II. It's the last line of defense.
And on the flip side of that, the vasodilators.
Bradykinin and histamine. These are usually involved with inflammation.
Histamine is the allergy one, right?
Right. If you get a bee sting, histamine is released by your mast cells. It dilates the local vessels, which makes it red, and it makes the capillaries leaky, which is what causes the swelling.
Why leaky? What's the point of that?
To let the white blood cells get out of the blood and into the tissue to fight whatever infection or venom is there. The swelling is a feature, not a bug. Bradykinin does something very similar. It's formed in the blood during tissue inflammation or maceration.
And finally, a lightning round on ions. The notes listed a few simple elements that can control flow.
Yeah, it's simple chemistry, really. An increase in calcium ions causes constriction. That's because smooth muscle needs calcium to contract. No calcium, no squeeze.
Potassium.
An increase in potassium causes dilation. It inhibits smooth muscle contraction.
Magnesium.
Powerful dilation. It also inhibits contraction. That's why magnesium supplements can sometimes help lower blood pressure in some people.
And hydrogen ions.
That's acid. An increase in hydrogen ions causes dilation. An acidic tissue is a tissue that's working hard and needs more blood flow to wash away that acid.
So let's zoom out for a second. We've covered a massive hierarchy here.
We have. It's helpful to think of it as different layers of management.
Lay it out for us. How does it all fit together?
Okay, so at the very bottom, you have acute control. This is the selfish tissues using their own waste products, their metabolites, to demand what they need right now, second by second.
All local workers.
Then you have the endothelium, that's the local manager, using things like nitric oxide to fine-tune the flow and protect the pipes from shear stress.
Okay.
Then you have long-term regulation, that's the construction crew, building new roads through angiogenesis or reinforcing old ones with remodeling, all based on chronic demand over weeks and months.
Right.
And finally, sitting on top of all of it, you have humoral control. That's the federal government, the central command, overriding the locals with powerful hormones to ensure the survival of the whole organism, no matter what the individual tissues want.
It creates this incredible balance where tissues almost never starve, but the heart never has to work harder than is strictly necessary. It's a beautiful, self-regulating system.
It really is. It is the definition of the wisdom of the body.
But, and this is where I want to leave our listeners today.
Yeah.
We talked about that wisdom being blind. We saw it with the incubator baby's blindness caused because the body adapted perfectly to an artificial, man-made environment. We see it with hypertension arteries thickening to protect themselves from high pressure, which ultimately makes the pressure worse and can kill the patient.
That's the catch, isn't it? The machinery is perfect, but the inputs can be flawed.
Exactly. The body adapts to the signal it receives, not to the intent behind the signal. It makes you wonder how many modern medical interventions or even just modern lifestyle factors are inadvertently triggering these powerful, ancient adaptation mechanisms against us. You know, we treat a symptom, but are we accidentally telling the body to build a road to nowhere?
That is the ultimate question for modern medicine, I think. We have to learn to speak the language of the body, so we stop setting it the wrong commands.
Something to chew on. Thanks for diving deep with us today.
A pleasure, as always.
We'll catch you on the next one.